Hello, welcome to Introduction to Composites. Today is the 5th day of this ongoing week, and over this week we have started discussing the stress strain relationship for especially orthotropic lamina, and in that context what we have seen is that there are 4 fundamental elastic constants, mutually independent elastic constants. And now in the last class we discussed the stress strain relationships for a generally orthotropic lamina, and there the number of elastic constants which we need to know are larger in number. And today what we will start discussing is the relationship between EL, ET, nu LT, GLT. These are the 4 constants for especially orthotropic lamina. So, we will relate these to the elastic constants for a generally orthotropic lamina. So, that is what we plan to do. So, first we will we will do this step by step. So, we will develop a relationship between Ex as a function of EL, ET, GLT and nu LT. So, this is the first thing. Similarly, we will develop a relationship for EY, MX, MY, GXY, nu XY, nu YX. Okay. So, we will do all this. So, how do we do this? So, what we will do is we will analyze lamina which is in a generally orthotropic case. So, here we are applying sigma x, we are not applying any sigma y, and neither we are applying any shear stress. So, this is my L direction, this is my T direction, and this is the value of theta. Okay. So, when I apply this stress sigma x, I can transform this sigma x in terms of in context of LT Cartesian frame, right. So, this is my x axis system, this is my y axis, right, this is my x and this is my y. So, in xy frame, what are the stresses? Sigma x 0 and 0, there is no stress in the y direction. In LT frame, what are the stresses? There will be sigma L, sigma T and tau LT. So, we have to transform sigma x in the LT frame, and we will use the transformation equations which we had developed earlier, I mean using these stress transformation relationships. Okay. So, in this matrix sigma x is sigma x, sigma y is 0, tau xy is 0, sigma x prime means sigma L, sigma y prime means sigma t, and tau x prime y prime means tau LT, and these numbers will be cosine square theta, sine square theta, 2 sine cosine theta and so on and so forth. So, using these transformation relations, we will find a relationship between sigma L, sigma t, tau LT and sigma x. So, directly using those relations we get sigma L, sigma t and tau LT is equal to sigma x cosine square theta, sine square theta and minus sine theta cosine theta. This is what we get. All other terms come out to be 0 because sigma y is 0 and tau xy is 0. So, let us call these equations A. Now, we know the stress strain relationship between sigma L, sigma t and tau LT, right. So, if I have to develop, if I have to calculate epsilon L, epsilon t and gamma LT, then what is this? It is sigma L over EL minus nu TL over ET times sigma t, and this is equal to sigma t over ET, and here we have the Poisson effect minus nu LT sigma L over EL, and here we have, so this is plus, and here we have tau LT divided by GLT. Okay. So, these are the relations we have already developed, and what is sigma L? Sigma L is sigma x cosine square theta. Okay. So, this I can write these relations as sigma x cosine square theta divided by EL, because sigma L is what? Sigma x times cosine square theta minus nu TL divided by ET, and sigma t is sigma x sine square theta. So, sigma x sine square theta, and then there is also a the third component will be 0, because there is a no component of sigma tau LT. Okay. The transverse strain epsilon t is what? Sigma x sine square, this is minus nu LT divided by EL times sigma L, and what is sigma L? Sigma x cos square theta plus next term sigma t over ET, and what is sigma t? Sigma x sine square theta. So, it is sigma x sine square theta divided by ET, and finally, we have tau LT is gamma LT is tau LT divided by GLT. So, what is tau LT? Tau LT is, as per this relation, minus sigma x sine theta cos theta. So, it is minus sigma x sine theta cosine theta divided by GLT. So, this is another set of equations, we call that B. So, what we have done now is we have expressed epsilon L, epsilon T, gamma LT in terms of sigma x, which is the external stress applied on the laminate in xy coordinate system, right. Now, so this is equation B. We also know from our stress transformation equations, these are the strain transformation equations, or if we are talking about engendering strains, these are the transformation equations. From this set of equations, we can express epsilon L, epsilon T and gamma LT in terms of epsilon x, epsilon y and gamma xy. In this case, we are going from LT coordinate system to xy coordinate system. So, theta is minus theta. Theta is minus theta. So, if we put the value of theta as minus theta in this matrix, then I can say, so I will write 3 more equations. So, I can also, so we can also say what can we say? We can say that, so we are going from LT coordinate system to xy coordinate system. So, epsilon x is equal to epsilon L times cosine square theta plus epsilon T times sine square theta minus gamma LT times sine theta cosine theta, and this comes directly from the strain transformation equations when we are dealing with engendering strains. Similarly, epsilon y equals epsilon s sine square theta plus transverse strain times cosine square theta and plus gamma LT sine theta cosine theta. And then the engendering shear strain gamma xy. Gamma xy is twice of epsilon L minus epsilon T times sine theta cosine theta plus gamma LT times cosine square theta minus sine square theta. So, this is equation, another set of equations, we call it equation C. Now, when we look at equation set B and set C, on the right hand side of C we have epsilon L and epsilon L. Okay. Similarly, we have epsilon T and epsilon T, and then we have the shear strain gamma LT, and these guys also appear on the left side of set B. Okay. So, this was epsilon T. So, this I will put it in green and this one is light blue. So, what I can do here is I can put, so let us say this is B1, this is B2 and this is B3, okay, B1, B2, B3. So, we will just work on B1. So, in equation B1, put epsilon L from C1, no, oh I am sorry, this should not be B1, B2, B3, it should be C1, C2, C3. So, this is C1 equation, C2 and C3, and this is equation B1, B2 and B3. So, in equation C1 put epsilon L from B1, epsilon T from B2 and gamma LT from what? Gamma LT from B3. So, once we do that, what we will get is, we will get a long expression which will involve only epsilon x. It will involve only epsilon x, okay, because it will involve on the, okay. So, it will involve on the left side, it will involve epsilon x, and on the right side it will only have sigma x, right, it will have only sigma x. So, we will get from that epsilon x is equal to sigma x times cosine 4 theta by EL plus sine 4 theta over ET plus 1 over 4 divided by 1 over GLT minus 2 nu LT divided by EL times sine square of 2 theta, this long thing. So, this is from C1. From C2, we get, okay, so before we do C2, and now what we do is we just divide both sides by sigma x. So, sigma x goes away from here, and here I get epsilon x by sigma x. And what is epsilon x by sigma x? this is nothing but 1 over Ex. So, this I will erase and I will call it 1 over Ex. So, this is my definition for 1 over Ex d1. Okay. Next, we are from C2. From C2 and of course, and B1, B2, B3, we do the same thing, you know. In equation C2, we plug the values of epsilon L, epsilon T and gamma LT and we get this thing, epsilon y equals minus sigma x gamma LT over EL minus 1 over 4 1 by EL plus 2 nu LT by EL minus plus 1 over ET minus 1 over GLT times sine square 2 theta. Okay. So, this is the stress, in the system in y direction caused due to stress in the x axis, on the x axis. Left side tells us that it is the strain in y direction, right side is the source term which is sigma x. So, sigma x is causing some Poisson's contraction also and that is why we have a negative sign here, right. So, if I divide both sides by Ex, essentially what I get is I can erase both these sides and what I get from here is nu xy divided by Ex. If I divide both sides, if I divide both sides by sigma x goes away from right side, on the left side I am left with epsilon y divided by sigma x and that I can express it as this thing. So, this is equal to this. So, now I have a definition for Poisson's ratio xy. Okay. So, we do the same thing and from C3 what do we get? We get gamma xy is equal to minus sigma x sine 2 theta times this whole long term nu LT divided by EL plus 1 over ET minus 1 over 2 GLT minus cosine square theta in brackets 1 over EL plus 1 over ET plus 2 nu LT divided by EL minus 1 over GLT, this is there, gamma xy. And if you see the definition, so if you apply a generally orthotropic, in generally orthotropic case, gamma xy is equal to minus mx times sigma x by EL. So, if you use this definition, then from this C3 you get mx. So, what is mx? So, you again divide both sides by sigma x and what you end up with is mx is equal to sine theta and then EL is already here. So, EL goes away and EL comes. So, everywhere the whole thing gets multiplied by EL. So, here it goes away and I have in the numerator, in the denominator it goes away and 2 EL. So, this is 1 over EL over GLT, or this one is redundant, just adds confusion. So, I will write it as EL over GLT. Okay. So, from C1, C2, C3 we get EX, relations for EX, nu XY and MX, which is the cross coefficient. So, this is D3. Okay. We can do similar things, and we will continue this discussion tomorrow, and what we will show is that using similar approach we can also develop a relationship between for EY and MY, EY, MY and nu YX, and then finally we will develop an expression for the shear stress modulus, the shear modulus GXY. So, that concludes our discussion for today. We will continue this discussion tomorrow. Until then, have a great day. Bye.